All living things require energy to function, but the ways in which animals acquire nutrients is distinctly different from other living organisms. Animals gain nutrients from eating, and in order to eat, they must forage for food. Foraging is searching for sources of food in the environment. The two goals of foraging behavior are to acquire adequate energy and adequate nutrients. However, foraging becomes a much more complex behavior when you look at the process. Nutritional need encourages foraging behavior. An animal's foraging behavior is affected by their need to balance the optimization of return, the risks of foraging, and conflicting homeostatic needs. Foraging for food is necessary for animals to grow, develop, and reproduce, but there are costs to foraging. An animal's foraging behavior must balance the benefits with the costs. We can predict animal foraging behavior with the optimal foraging model. The optimal foraging model states that an animal will choose the foraging pattern that yields the highest energy and nutritional gain while spending the least amount of time and energy doing so. For example, a bee will move to a new patch when the costs of staying outweigh the benefits. If the bee can do better somewhere else, it will move on. Travel time is one condition that affects the foraging model. The model predicts that the farther the patch, the more travel time required, and the longer the bee travels to reach the patch, the longer it will stay. Foraging behavior involves diet choice. In regard to diet choice, there are two defined species, generalists and specialists. A generalist can thrive on many different food sources. A specialist has a more limited diet and may only eat one or a few things. These diet choice specifications directly affect the foraging styles of different species. Animals can be categorized based on their trophic roles. Two trophic roles we will be discussing are herbivores and carnivores. There are costs and benefits to both of these trophic roles. Herbivores are animals that eat plants. For herbivores, their food is stationary and abundant, meaning it doesn't move and is high in quantity, so it is much easier to acquire. The defense mechanisms a herbivore must overcome to acquire food are mechanical and chemical defenses. Mechanical defenses include bark, hard shells, and thorns. They protect against herbivores by causing physical damage. When these mechanical mechanisms fail, plants may resort to chemical mechanisms such as toxins. Chemical defenses protect against animals by causing repellent odors, tastes, and may even cause death. Carnivores are animals that eat other animals. For carnivores, their food is mobile, meaning they have to catch it. This makes foraging for food more difficult, but carnivores' food is much easier to digest than herbivores' food. The defense mechanism a carnivore must overcome to acquire food are chemical, mechanical, and behavioral defenses. Much like plants, animals too use chemical mechanisms such as foul odors and poisonous toxins to deter predators. Animals also use mechanical mechanisms against other animals, such as a porcupine's sharp quills and a turtle's protective shell. Unlike plants, animals use behavioral defense mechanisms as well. An example of a behavioral mechanism is playing dead. Some animals, like opossums, pretend to be dead so that predators will avoid them. For carnivores, there are three methods for obtaining prey: active hunting, trap building, and sit-and-wait predators. Active hunting requires a lot of energy, but is also the least time-consuming method. It involves the process of locating, approaching, chasing, and subduing prey. In this example, a jaguar has located a sleeping crocodile and is carefully approaching. When he reaches the croc, he chases it into the shallow water and subdues it. There also may be cases where individual active hunting is not ideal, so animals hunt in groups. For example, the lions in this clip are working together to subdue a warthog. You can see one lion slowly approaching the warthog and then beginning the chase. This lion drives the prey towards a waiting lion, who then subdues the prey. The trap building method takes up some energy and time and involves building concealed traps in order to increase the chances of catching prey. In the Namib Desert, where the sands can reach a scorching 70 degrees centigrade, very little is able to survive, but the hot rod ant can amazingly thrive and even forage for food. In this tense encounter, an unsuspecting hot rod ant has strayed into an antlion territory and faces the ultimate test of survival. To build its trap, the antlion larva starts to crawl backwards, using its abdomen as a plow to shovel up the soil. By the aid of one front leg, it places consecutive heaps of loosened particles upon its head. Then, with a small jerk, throws each little pile clear of the trap. It gradually works its way from the outside toward the center. As it slowly moves round and round, the pit gradually gets deeper and deeper until the slopes reach an angle at which it will collapse from any slight disturbance. When the pit is complete, the larva settles down at the bottom, buried in the soil, with only its jaws projecting above the surface, often in an open position. Since the sides of the pit consist of loose sand at an intense angle, they afford an insecure foothold to any small insects that inadvertently venture over the edge, such as the hot rod ant. Slipping to the bottom, the prey is immediately seized by the lurking antlion, or if it attempts to scramble up the treacherous walls of the pit, it is stopped by showers of loose sand which are thrown at it from the larva below. By throwing up loose sand from the bottom of the pit, the larva also undermines the sides of the pit, causing them to collapse and bring the prey down to the center of the cone. The third method of hunting for carnivores is the sit-and-wait method. This method takes the least amount of energy but the longest amount of time. It involves a predator waiting for the prey to come to them. The alligator snapping turtle is a sit-and-wait predator. It sits at the bottom of the river with its mouth open and wiggles its tongue to lure prey. In evolutionary biology, an evolutionary arms race is a struggle between competing sets of co-evolving genes, traits, or species that develop adaptations and counter-adaptations against each other. These are often described as examples of positive feedback. The co-evolving gene sets may be in different species, as in an evolutionary arms race between a predator species and its prey, or a parasite and its host. The Red Queen hypothesis in biology states that species continually need to change to keep up with the competition. If a species were to stop changing, it would lose the competition against the other species that continued to change. If you take, for example, the relationship between a parasite and its host, both the parasite and the host are involved in an arms race with each other. There is pressure on the host to evolve to become resistant to the parasite, and there is pressure on the parasite to evolve ways to cope with the resistance of the host. Both species need to change genetically to keep up with the changes in the other species. The Red Queen principle creates this idea that species are never finished. Today we have discussed some of the many aspects of animal foraging behavior. This behavior is important because an animal's ability to forage affects its ability to survive and reproduce. We hope this documentary has opened your eyes to the intriguing subject of animal food selection and acquisition.